Imagine standing on Mount Everest, the roof of the world. The wind cuts through you, a relentless icy blast that chills you to the very core. And yet the world stretches out below, a breathtaking panorama of jagged peaks, a sea of mountains piercing the sky, and swirling clouds dancing around their summits. This is the highest point on Earth, a staggering 8,848.86 meters above sea level, like stacking more than 20 Empire State Buildings, one on top of the other, reaching for the heavens. But as you stand there, on that precipice of the world, a profound question arises in your mind. Why isn't it even taller? The tectonic plates beneath your feet are still pushing upward with immense, unstoppable force, building the mountain higher, millimeter by millimeter, year after year. So why hasn't Everest kept growing? Why hasn't it continued its relentless ascent, reaching ever higher into the sky, seemingly without end? What stops it? What prevents it from becoming even more colossal? Today we'll explore the silent but powerful struggle between the forces pushing Everest up, the relentless tectonic pressures from deep within the Earth and those holding it back, the forces of erosion, gravity. Everest isn't just a static peak, a fixed point on the map. It's a dynamic system, a living, breathing entity shaped by geology, the very bones of the Earth, physics, the fundamental laws that govern the universe. To understand Everest's height, we need to know how mountains form. Earth's surface is made of tectonic plates, giant slabs drifting on the mantle. When two continental plates collide, neither wants to sink. Instead, they crumple and thrust upward, creating mountain ranges. The Himalayas, including Everest, are the result of the Indian plate colliding with the Eurasian plate, a process that began 50 million years ago and continues today. Everest is still rising about 4 to 5 millimeters per year, thanks to this ongoing collision. But if the mountain-building engine is still running, why isn't Everest scraping the sky? Clearly, other forces are at work, pushing back against this relentless upward growth. The force keeps our planet's giants in check. One major reason, a fundamental constraint, Everest can't grow forever, reaching endlessly into the sky, is gravity, the invisible force that shapes our world. Gravity pulls everything without exception toward Earth's center, a constant, unwavering attraction, including mountains. Even the mightiest peaks are subject to its pull. As Everest gets taller, inching its way skyward, it gets heavier, its mass increasing exponentially. The weight of all that rock, that colossal mass of stone and ice, presses down, exerting immense pressure on the mountain's base, the very foundation upon which it stands. Imagine stacking toy blocks, one on top of another, build too high, reaching for the ceiling, and the base collapses, unable to bear the load, under the weight, the crushing force of gravity. Rocks have a limit, a breaking point, to how much weight they can support, how much pressure they can withstand, before they deform, before their structure begins to warp or break. Gravity acts as a natural governor, a self-regulating mechanism, setting a fundamental limit, a physical constraint on mountain height, dictating how tall these giants can truly become. The stronger a planet's gravity, the more powerful its downward pull, the shorter its mountains will be, held firmly in check by gravity's relentless grip. So, while tectonic forces, the immense power of the Earth's crust, push Everest up, driving it skyward, gravity constantly pulls it down, an opposing force, keeping its height in check, maintaining a delicate balance. Without gravity's limit, without this constant downward pressure, Earth's surface would look very different, almost unrecognizable. Unstable spires, precarious towers of rock reaching for the sky, defying all sense of stability. Gravity ensures mountains remain grounded and stable, within the bounds, within the constraints of structural integrity, preventing catastrophic collapse. It's a silent battle, a constant tug-of-war, shaping the landscape we see today. Gravity's influence goes deeper than just holding things down on the surface. It plays a crucial role in shaping the very landscape we see. This influence extends through a fascinating process called isostasy, a key concept in understanding how Earth maintains its equilibrium. Picture an iceberg. Only a small part floats above water, a mere fraction of its total size. The vast majority is hidden below the surface, a massive unseen foundation. Earth's crust behaves similarly, in a way that mirrors this iceberg analogy. It's essentially floating on the denser mantle, a layer of semi-molten rock beneath. When a massive mountain forms, through tectonic activity and geological processes, its immense weight pushes the crust down, deforming the Earth's surface into the mantle, displacing the material beneath. This is analogous to an iceberg sinking deeper into the water as it grows in size and mass. As Everest rises, reaching for the sky, its mass also pushes it downward into the Earth's mantle, creating a complex interplay of forces. This downward pressure offsets some of the uplift caused by tectonic forces. This dynamic interaction is what we call isostatic equilibrium, a delicate balance between the mountain's immense weight and the opposing buoyant force exerted by the mantle from below. Therefore, for every bit of height Everest gains through tectonic uplift, some of that gain is lost as the crust sinks further into the mantle, seeking equilibrium. This doesn't stop the process of uplift entirely, but it does mean that much of the upward push from tectonic forces is spent maintaining this delicate isostatic balance. Isostasy, therefore, is another way Earth keeps its mountains and other surface features from growing too extreme in height. Earth manages its surface features, its mountains and valleys, with remarkable balance, a testament to the power of natural equilibrium. While gravity and isostasy work from below, erosion attacks from above. Erosion by wind, water, ice, and temperature changes constantly wears down Everest. Ferocious winds blast the summit, while water seeps into cracks, freezing and breaking rocks apart. Glaciers grind down the slopes, carrying debris away. Avalanches sweep material off the mountain in dramatic fashion. Even as tectonic plates push Everest up, erosion shaves it down. The higher the mountain, the harsher the conditions, and the faster it erodes. Erosion is a relentless sculptor, always working to bring mountains back to sea level. With all these forces at play, is there a theoretical maximum height for mountains on Earth? Scientists estimate the limit is about 15,000 meters, almost twice Everest's current height. So why doesn't Everest reach this maximum? Erosion are incredibly efficient at keeping mountains in check. The higher a mountain gets, the more intense the erosion, making it hard to maintain extreme heights. Now, look beyond Earth. Olympus Mons on Mars towers 22 kilometers high, over twice Everest's height. Mars's lower gravity and lack of active erosion allow such giants to exist. On tiny Vesta, weak gravity lets mountains rise even higher to 22.5 kilometers. These cosmic comparisons show how a planet's gravity, geology, and atmosphere set the scale for its mountains. Everest is a giant by Earth's rules, perfectly sculpted by our planet's unique conditions. The story of Everest is the story of Earth itself, dynamic, ever-changing, and beautifully balanced. Thank you for watching. Your support are much appreciated, and I hope you found this video packed with info.